So we'll probably, well, welcome, good morning, blah, blah, blah. Nice work on the quiz. Look at me, all business today. Oh yeah, if we have time, I'll go through. Do you mean question 2 on the quiz? The one where you have to do a table of values? Yeah, got it. And we'll see if there's time. Otherwise, can hang back and I'll go through it. Okay, so, oh yeah, so we've got our test next week, and I do want to have a review class, but typically for this course, because we have so many tests, we don't actually do a review class. So it's kind of, I've made time for it, but because I really like to do review classes, but means we might have to shift some of the chapter 2 material till after the reading break. So, which is fine. We've got time. It's not that, it's just, I really wanted to get it out of the way. So that's my inner turmoil. But anyway, so likely only up till 2.3 for the test. If we can get through continuity 2.5, that would be great. We're not doing 2.4, which is the precise definition of a limit. So, so don't worry about 2.4 because it gets a little bit weird. All right, so let's see here. I guess I should start a new fresh page here. Oops. Haha, it knew what I wanted. I saw it also came up with margaritas, which is really funny. Because I can't remember the last time I had a margarita. Anyways, autocorrect. All right, so last day we talked about, just so some review, you used some limit laws, right? So we established some limit laws. Those are going to be really handy, right? Just for applying the limit. And essentially what you can do is you can spread that limit function across your actual function, right? And so you had to use some limit laws on the quiz today. And sometimes, right? So if we have applying the limit laws, to fractions, right? Or rational expressions. Rational expression is just a polynomial over a polynomial, right? And so, so when you apply the limit laws to a fraction, requires that the denominator is not equal to 0, that the limit of the denominator does not equal 0. For most of the problems, and you had a problem on the quiz, right? The last question I threw on there where, okay, I would end up dividing by 0. I know I can't do that. So what do I have to do? And so what we started doing last day was we started developing some ways that we can deal with this, right? And so let's see here. Did I? Oh yeah. Okay. So some ways to deal with this. Right, we said, well, our go-to, the first thing we're going to check, and what worked on the quiz that you just wrote, right, is factor and cancel, right? Look for a common factor of the denominator that's giving you grief. Yeah, I can, Jaspreet. Okay, so factoring and canceling is kind of your first stop, right? See if you can eliminate the problem by canceling it out, right? We said that as long as you're able to morph a function without changing the meaning everywhere else, then you're allowed to cancel. What else did we do? We tried kind of expanding and then factoring. So expanding and canceling. Right? Sometimes it just kind of depends on the question that you have. See what works. Okay, so that's the end of the review. But today, another thing that you could do is if you have a square root and you don't really know what to do with that in terms of factoring or canceling or whatever, then with square roots, what we can do is we can try rationalizing, right? So if there is, so here, it's an addition to the list, but it's new for today. So if there is a root, right? I'll say root, but I really mean square root, right? Typically, we can try rationalizing to change the layout of the function. Okay. For example, we've got, where are we? 2.3. So here, right, we finished off on example 5 last day, and we said, well, I see a 3 squared ultimately, and then -9, so I can cancel that, and then I was able to factor out an h, so that's great. So here, right, if I do example 6, copy, where are we? There, right? Going through that list that we just established here, can I factor out a t squared, right? Because notice, so I want to find the limit as t goes to 0, but I've got just t squared in the denominator, so 0 squared is just 0. So then I'm dividing by 0. So then I say, oh shoot, right? If we're not dividing by 0, you're allowed to just plug in the value and then that's your limit, right? But as soon as we're dividing by 0, we need to kind of regroup and figure out a different way to write this exact function, and then we can evaluate the limit. So I have this t squared. There's nothing I can do up here to try to cancel out a t squared. That would be my first move, right? Try to change this. Remember, right, the square root, as soon as we're adding or subtracting inside the square root, you can't distribute it. You can only distribute a square root over multiplication, can't talk today, multiplication or division, right? So if you're adding or subtracting in here, the root, you can't distribute it, okay? So that kind of doesn't leave us that many options, but then we remember, okay, well, if I want to kind of move around a square root, right? Here I've got the root in the numerator, so what I can do is I can rationalize the numerator. Remember, probably from a previous course, or definitely if you did pre-calc, potentially not if you're coming from Math 12, but pre-calc for sure, we rationalize numbers without any reason, but this is the reason. We say, oh, here's something that you can do. Here's some math that you can do. And then it's not until we get here where we say, okay, well, I don't want to be dividing by 0, so how can I manipulate this? One of those ways is to rationalize. Now, I'll remind you, because probably didn't stick, right? I don't blame you. But to rationalize a function, what we do is we multiply by the conjugate. So the conjugate radical, but I'll just call it the conjugate. So I'll just write a note here, right? So note, to rationalize a function, we multiply by the conjugate. I'll say radical because that's technically what it's called, radical conjugate, but I'll just call it the conjugate. So the conjugate for if you have the root of a plus b, the conjugate of that is the root of a minus b. And notice that the only thing that changed is that the plus changed to a minus. So in this case, right, I've got the root of t squared plus 9 minus 3. So in this case, the conjugate would be the root of t squared plus 9 plus 3, right? So you only change the addition or the subtraction. I'll show you with the simple version, but then when we also go through and do the calculation, you'll see why we do it. It shifts the root from wherever it is initially to the other position. So in this case, it's in the numerator, so it's going to shift it to the denominator. So what happens if you multiply by the conjugate, right? Then you have the root of a plus b times the root of a minus b. If I multiply this out, right, I get, so I'm going to expand this, I get root of a times the root of a. We know that's just a, right? And maybe I'll scoot this over so I can have it all on one line there. Root of a times negative b, so minus the root of a times b, and then plus the root of a times b, and then minus b squared. Notice once we cancel this thing here, right, we're just left with is equal to a minus b squared, right? And so we have eliminated the root, but we'll have moved it to the denominator. So in this case, right, so that's just kind of a review on rationalizing, because I don't expect you to have brought that in here, but the conjugate here is the root of t squared plus 9, and that's under the square root, plus 3. If I'm going to multiply the numerator by the conjugate, I can't just multiply by a number. I have to multiply by 1, right? And so I'd have to take the root of t squared plus 9 plus 3 over itself, right? So what does this look like? I'll put it on a fresh page here. Yep. I'm trying to find the limit as t goes to 0 of, I've got it here on the side, t squared plus 9 minus 3 over t squared. Sorry, I gotta go help my dog. She's struggle central. What's going on here? There. She's old, so sometimes she misses the chair, and then she just gets really upset about it and she doesn't try again. But she needs to get up there. So anyways. All right, so what I'm gonna do, right, is I'm going to change this, right? I'm trying to kind of get rid of the t squared in the denominator. So what I can do is I can multiply by the conjugate. So I get, this is the same as the limit as t approaches 0 of the root of t squared plus 9 minus 3 over t squared. And then I'm just going to highlight in a different color that when I multiply by the root of t squared plus 9 plus 3, I have to do it over itself so that I'm multiplying by 1, right? I'm just picking a convenient value of 1. And I'm going to emphasize that this is all one thing by putting brackets around it. You don't need them, but I find that they help. So now when I expand this out, right, and notice that this section also has brackets around it, right? If you just want to emphasize that I'm multiplying this thing, right, then we're back to FOIL, right? So, which FOIL itself doesn't make sense to me, but we're back to just expanding this thing. What is annoying is that we should be writing the limit each time, right? So the limit as t goes to 0. And I've got the root of t squared plus 9 times the root of t squared plus 9. For this time, I'm going to write it out. But generally, I would just go to, okay, well, that's t squared plus 9, right? So I'm just expanding this thing out. I am going to have to bump it over quite a bit. Try to. There. Minus 3t squared plus 9. And then, oh yeah, negative 3 times positive 3 minus 9. If I expand the denominator, I get t squared times the root of t squared plus 9, and then plus 3t squared. So if I kind of go through and I cancel, well, this is the same thing minus itself, right? And then the square roots up top are going to go away. So I end up with the limit as t goes to 0 of t squared plus 9 minus 9 over, and then t squared root t squared plus 9 plus 3t squared. I don't see anything. I've expanded the t squared in, so I guess I could pull it back out. I don't see anything jumping out at me that I could simplify this by, but I do see that I have 9 minus 9, right? And so when I do that, then I see, oh, okay, well, I guess I should have just kept the t squared outside because that's going to be a common factor that I'll be able to cancel as well, right? And so sometimes sometimes I'll expand stuff out and then factor it back together again, right? Just kind of be flexible. The limit as t goes to 0 of t squared, right? I'll just show 9 minus 9. And then because I see that common t squared, I'm going to pull it out right away, times the root of t squared plus 9, or maybe you never factored it in, or expanded it in rather, plus 3. Now I've got t squared over t squared, which is going to cancel to 1. So then I get the limit as t goes to 0 of 1 over the root of t squared plus 9 plus 3. this we can work with, right? So now that I've morphed this thing, now when I look, I can substitute t equals 0 in here, and I can still do legal math at every step, right? I have 0 squared plus 9 is just 9. And then when I take the square root, I get 3. And then I have 3 plus 3 in the denominator. So then what I get, right, is I get this is equal to, and now when I'm substituting in the t equals 0 here, I'm allowed to just drop it because that's when I'm taking the limit. So now I drop the limit notation and I say that this is the same as 1 over the root of 0 squared plus 9 plus 3, which is the same as 1 over 3 plus 3, 1 over 6. Yeah. Good. So that's another way, and I want you to have this one up your sleeve. I know it's kind of a reach, right? But it's going to come up, right? So if you see a root and you don't see any other way of canceling stuff, then rationalizing is going to be the way to go, right? So just kind of convince yourself, I guess. All right, so let's see here. All right, so now we're just gonna do some work kind of calculating limits. Let's do example 8. I've included the graph of the root of x over x. The root of x over x looks like this, right? Looks a lot like that Heaviside function. And we already said, okay, well, for a function to have an overall limit, then the left-hand limit has to equal the right-hand limit, right? And in this case, when we look at the graph, we see that it does not, right? But we want to prove it mathematically. So, oh, copy. Uh-oh, made a mess. My handout. I'll bring it in. Right, so here we can see that the limit does not exist, right? But we want to prove that the limit does not exist. So the key part of this is going to be to remember how the absolute value of x behaves, right? So the absolute value of x is a piecewise function. So we know that the absolute value of x is a piecewise function. Maybe I'll do a nicer curly bracket there, as if I have the option there. It's either going to be x if x is positive, right? So if x is greater than or equal to 0, then the absolute value of x, right? So if you're plugging in a positive value into the absolute value, you just get that value back, right? Whereas if x is negative, technically what you're doing is you're taking the negative of that negative, right? So then negative x is the absolute value of x if x is less than 0, right? And so that's how we produce these absolute values. But when we're using absolute values and we're reading absolute values, we just think, oh, I'm going to drop the negative, right? But technically what's going on is we're going to take the negative of the negative values. Okay. So what I want to show is that as x goes to 0, this thing does not exist. Now, remember, we want to prove that the left-hand limit equals the right-hand limit, or in this case, that the left-hand limit does not equal the right-hand limit if we want to prove that it does not exist. So what we're going to do is, we're going to try the limit as x goes to 0 from the right. So if we're approaching 0 from the right, we're coming in from positive values, right? And so that's going to be important because that means that the absolute value of x is going to behave like x from the right. Okay? So the limit as x approaches 0 from the right of the absolute value of x over x is going to be the limit as x approaches 0 from the right of x over x, right? Since we're coming in from the positive side. This, well, x over x, I can simplify to just be 1. Okay? So this is going to be the limit as x approaches 0 from the right of 1. Well, the limit of just the constant is just the constant. So that's going to be 1. Okay. And I'll make a note here that this is since x coming in from the right means that x is greater than or equal to 0. Maybe not equal to 0 because we can't have it equal to 0, but it does mean that x is greater than 0. Okay. So now you can probably see the pattern, right? So now if I'm coming in from the left, then I'm coming in from the negative values, which means that this absolute value of x is going to be replaced by negative x, right? So in kind of the same way x approaches 0 from the left of the absolute value of x over x is the same as the limit as x approaches 0 from the left of negative x over x, right? By the same logic. Which means, well, negative x over x is just going to be negative 1, right? So the limit as x goes to 0 from the left of negative 1, again, we're just taking the limit of a constant, which is just itself. So now, right now we can see, and we've shown mathematically, we've proven that the right-hand limit, it does not equal the left-hand limit. Usually we say it the other way, but it doesn't matter. Right, so these one-sided limits are not the same. So then we can conclude that the limit does not exist. Since the left-hand limit, does not equal the right-hand limit, right? So I'm going to use that shorthand we established last day, right? This is the same as saying 1 does not equal negative 1. That's true. We can conclude the limit does not exist. We can conclude the limit does not exist. Nice. Okay. Let's do another one, kind of similar. We'll do example 9. I've also included the graph of this function, just to help us see what's going on here. So kind of same idea here. If we've got this piecewise function, right? Now we've got the root of x minus 4 if x is greater than 4, and 8 minus 2x if x is less than 4. Notice that this function is not defined at 4, but that's okay, right? We talked about the limit doesn't actually care about what the function is at that exact point. It cares about how the function behaves around that point. So we're going to determine whether the limit as x goes to 4 of this piecewise function exists, right? And so here, right, we're going to be coming down from the left on this straight line, and then we're going to take off on this root function, or kind of come in on this root function rather from the right, right? It looks like we do have a limit. It looks like they approach the same value, but let's just show it mathematically, right? Because you're not necessarily going to have the graph, right? You're just going to have the function. So we'll just get right to it. The limit as x approaches 4 from the left, let's start at the left, of f of x is the same as the limit as x approaches 4 from the left of, and so if I'm coming in from the left, x is less than 4, then the function that I'm looking at is 8 minus 2x. So 8 minus 2x. We know from the limit laws, right? Hey, this is great. A polynomial, I can just plug in the value, right? And so we can just plug in the value here because it's a polynomial. So then this becomes 8 minus 2 times 4, which is 0, right? Which makes sense because we see that this line at x equals 4, the output is going to be 0. So that's what we would say the limit is based off of this graph as well, right? How about from the right? So the limit as x approaches 4 from the right of f of x. Well, now that we're coming in from the right, I've got the limit as x approaches 4 from the right of the root of x minus 4. Okay. As long as x equals 4 is in the domain of this thing, right? I'm restricted by the domain, of course, but as long as it's in the domain, I'm allowed to just plug things in. I'm just allowed to plug in x equals 4 here, as long as I'm not trying to take the square root of a negative number, right? In that case, I would need to manipulate it. But in this case, there's no need, because I end up with the root of 4 minus 4, which is the root of 0, which is 0. And to keep it on the same page here, we conclude that since the left-hand limit is equal to the right-hand limit, and I'll say it's equal to 0 just to show off how much I know, right? And I encourage you to do the same. We conclude, right, we've checked the left-hand limit, we've checked the right-hand limit. Even though it's not defined at 4, we can say that the limit of this thing overall at 4 is going to be 0. So we conclude, and just tiny, as x goes to 4 of f of x equals 0. Keep it on the same page. I wrote too lofty up above here. Oh well. Oh well. Okay. So let's see here. There's kind of one pretty big limit trick that we use, and it's called the squeeze theorem. And we mainly use the squeeze theorem for finding the limit of an oscillating function. So if we're talking about sine or cosine, right? So usually we're dealing with trig functions where they're just kind of oscillating like this. And if we've changed that sine or cosine function a little bit, then it's going to be hard to pinpoint what the limit is. But what we have is called the squeeze theorem. So there's a theorem that we kind of introduced before that on the handout, but it's the squeeze theorem that I care about. So I'm going to bring in both of these at the same time. And if you kind of read this first theorem, all it's really saying is that if the function f, right, so if the output of f at x is less than or equal to the output of g of x at x, right, kind of near a, but not necessarily at a, then the limits behave the same way, right? The limit as x approaches a of f of x is going to be less than the limit of g of x as x approaches a. So this is kind of a forgettable theorem. You don't really need it. I put it in there because that's what we're using down here, right? But just kind of, you can ignore this one. It doesn't really say ignore, does it? We use it for the squeeze theorem, but the squeeze theorem says that, okay, so now if I'm able to show that, let's say my function that I'm interested in is g of x, if I'm able to put bounds around that g of x with other functions, then what I can do is, if those other functions are easier to find the limit of, then if g is squeezed between these two functions that I'm able to find the limit of, and the limits of those two functions happen to be the same, well, the squeeze theorem says that, okay, if the limit of g of x is squeezed between a limit of L and a limit of L, there's no other option for the limit of g of x, right? And so here, right, the limit of g of x, if g of x is between these two functions, ends up being just the limit of the two bounds. So I will bring in these kind of graphs here. Because it is kind of good to see. Okay. So if you have a function g and you're able to establish a function h and a function f that wrap around this function, right, especially around the point that you're interested in, then you can leverage that to find the limit, right? So let's do an example. Of the squeeze theorem. Actually, I had a little blurb that I wanted to write down. Sorry, hold that thought. There, I had a blurb. I wanted to write down what I just said. So the main use for the squeeze theorem squeeze theorem is kind of fun to say and kind of a fun idea to think about. It's also called the pigeonhole sometimes, or yeah, the pigeonhole theorem, or there's a couple of different terms that you could use, but the idea is the same. You're just kind of forcing a function between two other functions. So the main use for the squeeze theorem is to find the limit, of an oscillating function with upper and lower bounds. With upper and lower bounds. think sine and cosine. Okay. So what happens is you're going to have this kind of big function involving sine and cosine. So something like this is how they're going to be laid out, right? So you've got this kind of nasty function involving sine or cosine. They'll behave the same way. What we need to, the first step here is to remember that, well, sine and cosine are restricted between -1 and 1, right? So they're just oscillating between -1 and 1. So then what we do is we build out this function, right? Or we build towards this function from the default sine and cosine. So here, right? To use the squeeze theorem, we start with the default sine and cosine functions, or sine or cosine function, depending on which one is in the question. Okay. So to use the squeeze theorem, we start with the default sine or cosine functions, which are bounded, right? So they're bounded on either end, bounded by -1 and 1. Yeah. And then we build up this function that we have in our problem. Okay? And it'll make more sense when I show you what I mean, but I just want to articulate it, what we're about to do. So, we then build up to the function of interest. So here, I see that I have a sine function in here with a bunch of other stuff, right? So that's what I'm going to build up to. But where I'm going to start is I'm going to start with just a plain old sine function. Okay? So we know that the sine of theta, and I'm just allowing for any theta here, right? So any angle is bounded between -1 and +1. Yeah. So that's where you're going to start, depending on, do you have a cosine or a sine in the function that you're interested in? But either way, it's going to look like this, right? So -1 is less than or equal to the cosine of theta is less than or equal to 1. Yeah. So then what I can do is, okay, well, how about I just let theta be 1/x, right? So then I've got this section out under control, right? The sine of 1/x. So this is going to be the same as saying that, therefore, I haven't changed my bounds yet. -1 is less than sine of 1/x, which is less than or equal to 1. Letting theta equal 1/x. All right, I'll do a little play-by-play on the side here. So now, right, what I've established here is that, okay, sorry, I have to scroll up a little bit. The sign of 1 over x is between -1 and 1. Okay, that's great, but I need x squared times that. So in order to get there, what I have to do is I have to multiply each side, right, or each piece of the inequality by x squared. Okay, so just remember that you're trying to get this to look like the function that you're given, right? And to get there, we're missing the x squared. And so we need to multiply through by x squared. Multiply through by x squared. So then that's going to be -x squared is less than or equal to the sine of, x squared times the sine of 1 over x, which is less than or equal to 1 times x squared, which is just x squared. Here, we've now built up the function that we're interested in, right? And we've established, we've followed, mathematical rules, and we've established that, okay, well, this thing is going to be between -x squared and +x squared. These two, -x squared and +x squared, those are easy to find the limits of, right? And spoiler alert, right? As x goes to 0, -x squared is going to be 0, or the limit. And the limit as x goes to 0 of x squared is also going to be 0. So then it's going to be squeezed between 0 and 0. So then we have no choice. The limit of this thing has to be 0. So we have built up, I'll put that kind of, that's just how I think about it, right? I start at my core function and then I build it up to where I need it to be. So we have built up to the function of interest. Okay. One thing that I guess I should note, but it's not going to be a problem typically, but when I multiply through by x squared, remember the problem with inequalities is if I multiply or divide by a negative number, then I have to switch the signs, right? But x squared is always going to be positive. And so here it doesn't change the inequality, right? And so here I'll make a note. Since x squared is always positive, we do not need to switch the inequalities. Just kind of a note in case you're multiplying. Now, I'm going to tell you, I'm not going to make you do that. That's way too much for you to keep track of, but it is something, kind of a mental note that you should have on hand, right? As soon as you're dealing with inequalities. Okay, so now what we can do is we have, if you refer back to the Squeeze theorem, right, we have f of x, g of x, and h of x, right? So this big function is squeezed between f of x and h of x, which happens to be -x squared and x squared. So now we can apply the limits, or maybe I should say the limit as x goes to 0. So here, right, the limit as x goes to 0, I have to do it on each part of my inequality, right? Oops, didn't keep my 0, or maybe I didn't write it, I don't know. has to be less than or equal to, of negative x squared, has to be less than or equal to the limit as x goes to 0 of x squared times the sine of 1 over x, which has to be less than or equal to the limit as x goes to 0 of x squared. Right. So we've forced this limit that's easy to calculate, right? And so here, the limit as x goes to 0, negative x squared is 0. Same thing with the positive x. So even though I can't really do anything about calculating this limit, I'm able to use the squeeze theorem to establish that, well, the limit is squeezed between 0 and 0. So by the squeeze theorem, this limit equals 0. Therefore, by the squeeze theorem, and you should say which theorem you're using, right? Especially if it has a name like the squeeze theorem. So then by the squeeze theorem, we conclude that the limit as x goes to 0 of x squared times the sine of 1 over x must be equal to 0. Nice. So that's the squeeze theorem. That's the end of 2.3. I don't think that we should start a new section with what, 5 minutes left in class. No, I think we'll end it there. So I'm working on a practice test for you guys for the test on Thursday. And then, but I'll send out an announcement as soon as it's available, okay? Usually I make them a little bit longer than the actual test because I want you to see all the different versions of a question, right? So sometimes I get a little bit overly ambitious, but just kind of keep that in mind. It'll be a little bit longer just so you've seen all the scenarios. All right. Any questions before I let you go for the weekend?
Well, there's Jaspreet's question about the number 2 on question number 2 in the quiz.
Oh, yeah, sure. Yeah, we've got time. Why not? So we've got.
Thank you.
Thank you. I totally forgot. Quiz number 3, question 2. Let's see, I actually have it. I'll just go there here. So all our numbers might be a little bit different from each other's, but, well, maybe not for this one. Okay, so on my end, it says use a table of values. Oops. To estimate the limit. And then, of course, it says if you have a graphing device, blah, blah, blah. So if I want to know the limit as x goes to 6 of the natural log of x minus the, well, that's the ln, right? The ln of 6 over x minus 6. Here, right, I have that problem where if I just plug in x equals 6, I run into trouble. I'm dividing by 0. I don't want to do that, right? And so this is where I said in the instructions at the top, you only need to find 2 values. The trick is to find 2 values that are sufficiently close to 6, right? And so for me, what I would do is I would have, okay, I'll set up a table of values like this. And I'm going to pick a value to the left of 6, right? So maybe I'll do 5.99. Close enough, right? I like to go as close as I can without making my calculations really tedious. So it's a fine balance. And then I'll pick a value to the right of 6, right? So maybe 6.01. Okay. And you can do lots more values, but it's really time consuming, so no thanks. All right, and then here I'll have f of x is equal to the ln of x minus the ln of 6 over x minus 6. In this case, I'm plugging in x equals 5.99, right? So I'm gonna have, and maybe I should have, I'll give myself 2 rows. So then here, f of x is gonna be the ln of 5.99 minus the ln of 6 over 5.99 minus 6. And if you just do that on your calculator, what do I get? Ln of 5.99 minus the ln of 6 divided by 5.99 minus 6, I get an approximation of roughly 0.1668057101. Oh, cut me off there, but that's okay. It says to 3 decimal places, so no biggie. And then if I do the same thing for 6.01, I have the ln of 6.01 minus the ln of 6 over 6.01 minus 6. That's going to be, and if I just do it here, 0.1 minus the ln of 6 divided by 6.01 minus 6, I get roughly 0.1665, phew, 279319. What did I say, phew? Because to 3 decimal places, these 2 round to the same thing. Right? No, so you don't average them, but you do look at to 3 decimal places here, right? This is going to be 0.167 to 3 decimal places. And that's the same. So you don't want to stop. So you would have to, if they don't round to the same value, you would have to do more values closer to 6, right? But because here they round to the same value, the answer is 0.167. So our guess. We estimate, oops, the limit to be 0.167. Does that make sense?
Question, not related to this. Do you have office hours today or no?
Not today.
Okay.
And I actually have a couple of meetings after this, but
Okay.
I do have office hours on Tuesday, but I'm also free anytime on Monday. So
Well, I was going to be a bit late because as I was looking for a little clarification how to do some of one of the quiz questions. But yeah, we're running over time, so.
Yeah, so yeah, today, usually I'm free after class on Fridays, but today I've got a meeting and then
Some bad luck, whatever. I'll handle it. One way or the other.
But do you want me to let you know when I'm free? If you send me a text, I can text you when I'm free.
That shouldn't be an issue. I've got a thing later today I need to be dealing with as well. So, all right, no problem.
What a day, right?
All right. In that case, ta-ta. See you Wednesday.
Sounds good.